Okay, let's start with page 429, number 59. And turning your books to that particular problem, it has to deal with, actually it's on page 430, and it has to do with a weight gain of a calf. And they give you a differential equation, dw over dt equals k times 1200 minus w. All right, so let's just take a minute. I'm going to come back to this problem. I'm going to talk about our differential equations and our solutions. And it'd be good if you just have a sheet that you can make to have all these together. So if your differential equations in the form of dy equals ky dt, and I think on my other notes I left off that other rate of change variable. The solution will be y equals c e to the kt, and the graph looks like this. That is growth. And we think we had a couple of decay models also that we looked at. And those would be probably in the form of, just off the top of my head, negative ky dt will give me a y equals c e negative kt. And we'll verify that when we talk about our notes. And it'll look like this. But we know it has to be a negative exponent there for it to be decay. All right. Then the next one we talked about fits into Newton's law of cooling. And that was dy equals k y minus a value. And this would be initial temperature, surrounding temperature, current temperature. This is going to be worded kind of several different ways. We'll look at several different type problems when we start reviewing Friday and Monday. And its solution looks like y equals c, value, your beginning value, plus c e to the negative kt, because it's going to have a value that is going to come down toward. So this is just how it shifts up, and this is going to be the declining value. The next model we look at is going to be limited growth. And limited growth was dy equals k, and it's just in the other form, value minus y dt. And its solution always going to be y equals value minus c e to the negative kt. And its graph is going to look like this. And then our logistic growth. And sometimes we call that carrying value. And it is dy equals ky 1 minus y over L. And its solution is y equals L over 1 plus b e to the negative kt. And its graph is going to have a limited top to it, quick growth, and then levels off. So these are each of our models, and each of the problems that we have to fit into one of these differential equations and one of these solutions and look like one of these graphs. So once you recognize the forms, it makes it easy to know what your solution should look like. So going back to number 59 on page 429, then we know this is going to be one with limited growth. We know that before we start because it fits that model. So before we even start this question, we already know that this is going to have some starting value, and it's going to top out about 1,200 pounds at 1,200, which kind of makes sense. We can't have an industry where animals keep growing indefinitely to bigger and bigger values. That would be unhealthy, and they wouldn't be able to exist in that form. Okay, so we know that at birth, so initial, when t equals 0, the calf weighs 60 pounds. And we already know, since this is a limited growth, that I'm not even going to anti-differentiate. I'm going to go ahead and just put it in its form. W equals 1200 minus C e to the negative KT. I'm going to go straight to the form. All right, so plug in 0 for T. That means that becomes 1. 60 is the weight. And we find that the value of C is 1140. So my solution is W equals 1200 minus 1140 e to the negative KT. All right, so that is the solution for part A. All right, part B says, still on part A, we're going to use the different values for K. So it just wanted you to use your calculator and plug in first 0.8 and then we're going to plug in negative 0.9, and then you have negative 1. All right, and it asked for, let's see, to graph the 3 solutions, so you can look at these solutions on your calculator. All right, so we took the differential equation. I didn't do a separation of variables. We went straight to the solution. Here's the form of solution. Then we plugged in the K values they asked for. All right, part B. Part B says that the amount of the animal is sold when its weight reaches 800 pounds. Find the time of sale for each of the models in part A. So you would say 800 equals 1200 minus 1140 e to the negative 0.8 t. And you subtract 1200, divide by negative 1140, and take the natural log of both sides and find t. So when t is equal to negative 0.8, you're going to find the year that, when k is equal to negative 0.8, t would be approximately 1.31. So take your calculator and take the time to do that and see if you get those values. And then when k equals negative 0.9, t is approximately 1.16. And when k equals negative 1, t is approximately 1.05. And these are years. And then weight will max out at 1200 because that is our limiting value. All right, I'm going to stop this video and then I'm going to work page 429, page 430, numbers 72, 75, and a couple of others on that page. I'll write them on, I'll adjust your assignment calendar and have those listed correctly on your assignment calendar.